Let us see about bimolecular nucleophilic substitution reaction, that is SN2. What is substitution reaction? Substitution reaction is a reaction in which a group is replaced by an atom or group of atoms by that is called substitution reaction. Okay, which type of compounds undergo substitution reaction? The organic compounds that have an electronegative atom or group bonded to an sp3 hybridized carbon undergo substitution reactions. So the bond will be a polar bond. Okay, see the reaction RCH2 CH2X plus Y minus ion, that is Y minus here acts as the nucleophile and that is replaced, that is X is replaced by Y minus. X is replaced by Y. Here this bond between the carbon and X is a polar covalent bond. So easily that X can be replaced as X minus ion and that Y can come and substitute in that position. So this reaction is called a substitution reaction. So the electronegative atom or group is replaced by another atom or group. Okay. Now in this case we have seen only the halogens, halides, organohalide compounds. Why organohalide compounds react? Why alkyl halides alone undergo substitution reactions, or particularly alkyl halides undergo substitution reactions? The reason is that because it is having a partial negative charge, that a halogen has a partial negative charge and the carbon has a partial positive charge. And so what happens? The carbon halogen bond is a polar bond and so substitution reaction takes place very readily and the halogen can be either a fluorine atom, chlorine atom, bromine atom or iodine atom. Anything can be replaced. So alkyl halides undergo substitution reaction. Now coming to the mechanisms for the substitution reactions, there are two important mechanisms. The first one is that a nucleophile is attracted to the partially positively charged carbon, that is an electrophile. Okay, so here what happens is this electronegative element, that is X which is having a partial negative charge, is removed as a minus ion, and at the same time when it is removing, the nucleophile comes and attacks the carbon which acts as an electrophile. Okay, and this reaction takes place in a single step and this is called the SN2 reaction, that is bimolecular nucleophilic substitution reaction. And here you can see in the picture, that is the carbon being an electrophile and carbon plus and then halogen that is removed and the nucleophile comes and attacks that carbon, and that now the product is a substitution product in which the place of X is replaced by a nucleophile. So this is SN2 reaction. This we'll see it briefly in our video. And the next I'll give a small thing about SN1 reaction also. See here what happens is the carbon halogen bond breaks heterolytically without any assistance from the nucleophile. That is that the reaction, first what happens is the halogen leaves the place and we get a carbocation, and that in the second step the nucleophile comes and approaches the carbocation and it forms a bond. And so this reaction takes place in two steps and this is called unimolecular nucleophilic substitution reaction. This we shall see it briefly in our next video. Now I'll concentrate on SN2 reaction. Now we'll move to the mechanism of SN2 reaction. See this mechanism here, we are saying it is as SN2. So that is bimolecular nucleophilic substitution. So the mechanism is always studied by using the kinetics, the factors that affect the rate of the reaction. That says the mechanism, that from that only we can determine the mechanism of the reaction. The rate of a nucleophilic substitution reaction, we can say it depends on the concentration of both the substrate and the attacking group. Here the substrate is methyl bromide and the attacking group is OH minus ion, that is the nucleophile. And here the rate of the reaction depends on concentrations of both the reagents, that is methyl bromide and hydroxide ion. See how it depends. If the concentration of methyl bromide in the reaction mixture, if you are doubling that reaction, if you are increasing the rate, increasing the amount by 2 times, that is if you are doubling the amount, the rate of the nucleophilic substitution reaction also doubles. If you increase the concentration of OH minus ion, or if you are doubling the concentration of OH minus ion, then the rate of the reaction also doubles. So if the concentration of both the reactants are doubled, then the rate of the reaction quadruples. So what is the meaning is, the rate of the reaction depends on the concentration of both the alkyl halide and the nucleophile, that is both the reagents. And so the reaction is called the second order reaction. You can see the example here, that is conversion of methyl bromide to methyl alcohol. Here the reaction depends on the concentration of methyl bromide and hydroxide ion. So okay, now we'll move to the next step. Here the rate law tells us which molecules are involved in the transition state of the, so only by seeing the rate law we can study the mechanism of the reaction. Okay, so what we have understood is the transition state of the reaction, that is the transition state, that is the rate determining step of the reaction is a slow step, that is the slow step, and that step involves the concentration of both methyl bromide and hydroxide ion. So we are saying that this is a bimolecular reaction. So we can say this SN2. You can see this as S stands for substitution and N stands for nucleophilic and 2 for bimolecular. Okay, so here the reaction, that is the both the reagents, that is methyl bromide and hydroxide ion, are involved in the rate determining step, and so this reaction is a bimolecular nucleophilic substitution reaction. Okay. Now we'll move to the mechanism, that is Edward Hooke, that is the mechanism was given by the scientist Hooks, that is Edward Hooks and Christopher Ingold. They gave a mechanism. You can see the mechanism. See, it is a concerted reaction. Concerted, what is the meaning? It is the reaction takes place in a single step. That is no intermediates are formed. That is the main point. Then second step, that is the nucleophile attacks the carbon bearing the leaving group and displaces the leaving group. What is the meaning is, now what happens, the same step, both the hydroxide ion and the substrate is present, and that hydroxide ion attacks the substrate from the side opposite to that of the side bonded to the leaving group. So here the leaving group is bromide ion, and that leaves from one side, and the OH group is attacking the carbon from back side, and so here the main thing is the reaction is backside attack. The reaction takes place by backside attack. So here you can say the carbon is said to undergo backside attack. This is the mechanism proposed by Hughes and Ingold. And now, why does the nucleophile attack from the backside? That is an important point. The simplest explanation is given by the molecular orbital theory. So you can say here, see, in the case of backside attack, the nucleophile, usually for a reaction to take place, the HOMO, that is the highest occupied molecular orbital, must combine with the LUMO, that is the lowest unoccupied molecular orbital. That is the molecular orbital theory. And here if you see a backside attack, here the nucleophile contains H, that is HOMO, the filled non-bonding orbital. The filled non-bonding orbital of the nucleophile combines with the empty and sigma star antibonding orbital of carbon. So what happens? They are in phase, that is the bonding interaction takes place, and so the reaction will take place very quickly. But in the case, if the same thing, if the nucleophile is approaching in the place where there is the leaving group, that is where there is Br, then what happens is this bonding will be, see here, it is an out of phase antibonding. It is an out of phase antibonding. See, this you can understand. Out of base antibonding interaction, and here it is in phase with the bromine atom which is going to leave. So this front side attack is not at all possible. So always what is possible is the backside attack. If the reaction takes place in a single step, only backside attack is possible. And so what happens? The nucleophile always approaches an sp3 hybridized carbon on its backside. Okay, now we'll move to see what happens, how the Hughes and Ingold, they have given the mechanism according to this one, according to the molecular orbital theory. That is the evidence given by molecular orbital theory. They supported, they supported, by the way, see the mechanism, Hughes and Ingold's mechanism. The mechanism shows the alkyl halide and the nucleophile coming together in the transition state of the one-step reaction. See the bromine atom, it is leaving, forms a transition state in which the carbon is pentacoordinate, or you can say this carbon is that is pseudo pentavalent. The term we can say it as pseudo pentavalent because it has, that is, 3 covalent bonds and one bond is being partially cleaved and the other bond is being partially formed, and so this is the transition state formed. And see what happens in the product. The Br is removed and OH is attached, and also you can see the energy profile diagram that is called as the reaction coordinate diagram, and delta G ash will shows the amount of activation energy required for the reaction to takes place, and so this is given in the figure. Now the figure shows that the nucleophile attaches. This figure also you can easily understand how the backside attack takes place. See what happens. This is a tetrahedral sp3 carbon and that Br group is leaving and that the OH group is approaching, and this is the oxygen atom. When the OH group approaches, what happens to, see this bond? This bond becomes that is they are in plane. They are in plane with each other, and so they becomes pseudo pentavalent, or it is called pentacoordinate, and this is the transition state and it becomes planar. The transition state is planar, and so you can see this partially cleaving bonds and the partially forming bonds. And then what happens in the next, what happens after the transition state? When a transition state changes to this again the carbon becomes sp3 hybridized carbon, and so what happens, this oxygen binds with this carbon, and so here if you see the configuration, if you start with the plus, if you start with the D form, you will get a L form compound. So that is totally inversion of configuration that I have shown in the next video, next PPT. See this, the carbon inverted its configuration during the course of the reaction. This is the way how it is, how it was explained by Walden, the scientist, just as an umbrella which is inverted in a windstorm. See, when you are going out during a windstorm, what happens when you are carrying an umbrella? The umbrella turns upside down. The same way, this methyl bromide, if you start with the plus form, you will be getting methanol, where they will be getting the compound which is in the opposite configuration, that is inversion of configuration. And this was given by the scientist Paul Walden, and this is the main explanation for this is the main things about the stereochemistry of SN2 reaction. So because an SN2 reaction takes place with inversion of configuration, only one substitution product is formed. That is also very important. Only one product is possible. So starting with the D form, you will get an L form whose halogen atom is bonded to an asymmetric carbon, undergoes an SN2 reaction. See the configuration, you can see this in this picture. I have taken a carbon which is having a chiral center, and this carbon, if you are starting with the D form, and the product will be, after a nucleophilic attack in SN2 reaction, the product will be surely an L form. Thank you.